Welcome to Chapter 12, Types of Bonds. The reason we need to learn about types of bonds is so we can learn about the shape of a molecule. The shape of a molecule will actually determine how a molecule behaves and a lot of the physical properties. Knowing how a molecule is shaped, I should say, allows us to determine many of the physical properties such as boiling point, viscosity, surface tension, melting point, vapor pressure. All of these are physical properties. For example, one of these molecules might be a medicine. If you look on the sides of some pill bottles, before the name of the medicine, it'll say L for a left-handed molecule or R for a right-handed molecule. The other one, well, that could be a poison. At some point, you should have learned about a picture like this in biology class, where if the molecule doesn't fit, and they call this the Lott-Key method, correctly, then the molecule, the chemical reaction won't take place. Again, it's based on the shape of the molecule. Before we do that, I need to review the three types of bonds that we have. The first type of bond is ionic. The second type we're going to talk about is covalent. And the third type I don't spend much time at all talking about, even in AP, and that's metallic bonding. But you should still know it exists. First, we need to define what a bond is. And a bond is simply a force. And that's kind of difficult for us to envision. See, remember, atoms are mostly empty space. And that's hard to visualize. And so here we have an empty space held together by a force creating a compound. It's much, much easier to visualize a bond as a stick. That's what these two sticks represent, are bonds. But all they are is a force, and it holds the atoms together and makes them function as a single unit. Bond energy is the amount of energy we need to break a bond. So the more energy we have to put into breaking the bond, the stronger the bond is. Ionic bonds have the strongest bond. Obviously, what's pictured here, this is not ionic. Water is a covalent bond. Ionic, as I said before, is the strongest. If you remember from a while ago, an ionic bond is between a metal and a nonmetal. And what happens with this is the metal loses an electron. And when that electron is lost, I've lost an electron. Well, are you positive? Well, yeah. So this metal becomes positively charged. In this case, I have lithium, and that's a cation. And when it gains an electron, it becomes negative, and that's gain, and that's an anion. This force between the two, does anybody remember what that force is called? It's an electrostatic attraction. I've seen places before where they don't even call, they being the people's not smarter than I am, don't even call an ionic bond a bond, because technically a bond should be shared electrons. And here they're not even sharing, they're just a couple of, somebody's stealing, it's a thief. However, most of the scientists say it is an ionic bond, even though somebody completely steals the electron, and they're drawn together by this opposite charge attraction thing. I like this GIF because it nicely shows the sodium atom becoming a sodium ion by losing an electron. And then the chlorine becomes an anion by gaining the electron. These oppositely charged ions then are drawn to each other by an electrostatic attraction. And I like this picture even better because look at this. You got sodium and chlorine. They each have their own bone, right? Each of the dogs has a bone, and chlorine is going to take that bone away from sodium. Total stealing of, in this case, the bone, representing the electron. And then once those atoms become oppositely charged, they attract. We got to let it play one more time. There he goes. Mine. In a covalent bond, electrons are shared. Yep, shared they are. Now, they share electrons so that they can have typically 8 valence electrons, because who has 8 valence electrons? That's right, the noble gases. Well, that's true for most of them, but not for hydrogen. See, because hydrogen would really, really, really like to be like helium. And even though helium's a noble gas, in the first energy level, it only has an s orbital, so that only holds 2 electrons, which is how many helium has. So hydrogen is happy when it actually shares just 2 electrons. Otherwise, everybody else, with 1 or 2 exceptions, but for the most part, everybody else wants to share 8. These 2 atoms will come together, and when they do, they end up sharing electrons. The actual bonding releases energy, and if I were to break it apart, it would have to absorb energy to break the bond. But when these 2 atoms, which I believe are both fluorine because they both have 7 outer shell electrons, now they both think they have 8. And they can both feel like a noble gas. Here we have the dog analogy again. So we have 2 dogs coming in with bones. The bones are obviously the electrons. And they each come in and nobody steals. They're going to share those electrons. That's a covalent bond. Watch it one more time. Here they come, sharing the electrons. The types of bonds that we deal with are ionic bonds and covalent bonds. Ionic bonds are made up of a metal, which will become a cation, and a non-metal, which will become an anion, and they stay together because opposites attract, and that opposite attraction is called an electrostatic attraction. The covalent bonds share electrons, and you need 2 electrons per bond. However, they don't always share equally. Nope. Yeah, there's types of covalent bonds. Yay! I know, you're excited. How we get from a covalent to polar covalent and ionic compounds, it's a spectrum, in the same way that the visible spectrum is a spectrum. When we covered visible light, we had a million different shades as you go from red, orange, yellow, green, blah, 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 blah. It's not like, oh, look, here's a red and here's an orange and here's a yellow. That was like the emission spectrum, discrete steps. Well, the types of bonds is a spectrum like the visible spectrum where you have this sort of blending from one to another. There's no specific, well, if you're here to here, you're purely covalent, and here to here. It's more of a spectrum, and for our purposes in Gen Chem, we just need to kind of have more of a feeling between them. As much as I like this picture for a spectrum, I am going to change this word up here. Instead of pure covalent, they're usually called non-polar covalent. Then we have polar covalent bonds, and then we have ionic bonds. Now see where it says 0, low, and high? That's all based on this concept called electronegativity. And I'm going to talk about, not you, but I'm going to talk about electronegativity in a minute. But the idea is if something has a 0 or very close to 0 electronegativity, we say it's nonpolar. If something has a low electronegativity, difference is the key word, it's polar covalent. And if it has a ginormous difference of electronegativity, it's ionic. Okay, so how are you going to tell the differences in electronegativity should be the burning question on your mind now. Well, basically, there's the same thing, but it's in words. The definition of electronegativity is the ability to draw electrons to itself and away from somebody else. So it's basically the ability to steal electrons. If you have an extreme difference, it's ionic. Moderate, we consider you polar, and no electronegativity difference, well, I've got pure covalent there. Yeah, I prefer nonpolar. Nonpolar. I've seen it both ways, but I do prefer nonpolar covalent. One of the things we do in AP is we actually look at the electronegativity values. And we're not going to do that in Gen Chem. I know, you're welcome. But what you do need to know is, see this guy up here? Fluorine? He is the most electronegative. Remember we said he also had the highest ionization energy? He's the hardest one to take an electron away from. And he is the one who wants electrons the most. He wants them bad. He wants electrons big time. And he's got this unbelievable ability to take them away. And if you recall, fluorine also has a very small radius. It's very, very small atom. He's got a very high effective nuclear charge, which is part of the reason he's small, has a high ionization energy, and is extremely electronegative. Super wants electrons. Cesium down here, not so much. It's a really big atom. Its effective nuclear charge as compared to anything else in its row is not as big. It has a low ionization energy, and it has a low electronegativity. If you guessed that the electronegativity trend is identical to that of ionization energy, you are exactly right. Most, and way down here, least. And the trend, just like ionization energy, sort of an arrow all the way up to the fluorine corner. What we're going to be looking at is how two different atoms on the periodic table share electrons. And basically the rule is the farther away from they are on the periodic table, the worse they share. So if we were looking at francium and fluorine, this guy is one great big old hog. This guy, not so much. So they do not share well. And in fact, they don't share well at all, to the point it's ionic. Fluorine's going to steal that electron away from francium. The farther the two atoms are, the worse they share. The more likely they are then to be ionic. This is another good example, hydrogen and oxygen. They don't share very well at all. Now see all these pink dots? That's called an electron cloud. That's where all of the electrons of both oxygen and hydrogen are shown around this entire molecule. Oxygen is much more electronegative than hydrogen. By the way, yeah, hydrogen doesn't sit where hydrogen sits on the periodic table in terms of electronegativity. Hydrogen is equal to phosphorus in terms of electronegativity. And I'm abbreviating it. But they have the same electronegativity value. However, oxygen, being closer to fluorine, it's a big ol' hog. In fact, there's 3 hogs. NOF. These are the 3 biggest electronegative hogs on the periodic table. And the farther something is away from one of these, the more greedy these 3 guys get. And that's shown by this electron cloud, where oxygen's taking all of the electrons away from hydrogen, making this side of the atom, this side of the compound negative, And this side of the compound, much more positive. And that actually matters for physical properties. Then I have another picture here to show you. Hydrogen and fluorine. Who's the big old hog in this one? That's right, fluorine, because NOF. Those are the three big hogs. Fluorine's the biggest. Fluorine here is stealing all the electrons that are available to the two of them away from hydrogen, which means this side of the molecule ends up negative and this side ends up more positive. So that's why we call this one polar. If you can see, there's a pole on this side and a separately charged pole on that side. They're still sharing, so that's why it's called polar covalent. This is a pretty nice visual image. Here we have non-polar covalent. These two are sharing perfectly. A and B, you can see the electron cloud is distributed evenly around both A and B. And generally the rule is for non-polar covalent, if they are the same, and mind you, this is covalent, so that would be non-metals, because that's covalent, non-metals, they're sharing electrons. So if they're the same, or say hydrogen, phosphorus, or right next door, even oxygen and fluorine, they would share pretty well. Both of these guys are big-time hogs, but they're both big-time hogs. So that electron cloud around hydrogen and phosphorus, oxygen and fluorine, or even chlorine and chlorine, because they're identical, share perfectly. Then we have polar covalent, and in this case these guys aren't sharing at all. In this picture above, who's the bigger hog? If you said B, you are correct. B is much more electronegative. It is stealing most of that electron density away from oxygen. So this side becomes more negative and this side becomes more positive. And the farther apart these two atoms are on the periodic table, the more somebody is going to be greedy. How greedy? Well, that's a very good question. For our rules in Gen Chem, we're still looking at two nonmetals. That didn't come out very well. Two nonmetals, which is a good rule for us in Gen Chem. And again, these are also nonmetals. Now, the ones that don't even share, they're ionic. Cation, anion, electrostatic attraction, metal with a nonmetal. In this particular dog picture, you can see, yes, they're still sharing those two bones, so they are covalent. But fluorine, or the Great Dane looking dog in this one, is much greedier. It's got a much bigger hold on those two electrons than the hydrogen dog. Non-polar, no, I lied, I said that wrong. It is polar covalent. They are not sharing equally at all. Okay, so we're going to take a look at a whole bunch of these different bonds and decide who is, and that's the real question. We're trying to figure out, in this case, who is going to be non-polar covalent. That's a C. Covalent and ionic. And this says in order of increasing polarity. And since this one's the biggest, that's what should be on this end, and non-polars on this end. Again, we do just kind of got to keep in mind that for the electronegativity trend, hydrogen does not sit here. Hydrogen and phosphorus sit in the same spot. All right, well, in this case, we have two hydrogens. They're identical. So what's your guess? If you said they're non-polar covalent, you are correct. Oxygen and hydrogen. Well, oxygen is right here, so let's wait on that one. Chlorine and hydrogen. Then we have sulfur and hydrogen. Hey, these guys are neighbors. Sulfur and hydrogen are neighbors on this one. So, our first one is going to be hydrogen-hydrogen. That is clearly nonpolar covalent. The next one we have then is sulfur and hydrogen. Those guys are neighbors, so they're going to share pretty well. And I know that fluorine is the biggest hog on the periodic table, so that one's got to be way over here. I'm not sure that it's ionic, but it certainly is not going to share well because fluorine's a great big old hog. So we've got those gone and that one gone. Now I just have to decide between these two. Well, oxygen's one of the other hogs. It's not quite as big of a hog as fluorine, but it's pretty big. So that one's going to go here. And then it leaves us with chlorine and hydrogen in the middle. Now, none of these are ionic, but in terms of increasing polarity, this is your nonpolar end, this is your most polar end. Now, in this case, we want to choose a bond that is more polar. And the first thing I want to do is I want to put hydrogen kind of where he belongs on the periodic table, so we know hydrogen and phosphorus both sit there. Well, look at that. Hydrogen and phosphorus. If they both sit in the exact same position, you can consider them identical. So that's going to be nonpolar covalent. H and C, well, C is farther away than that. So this one is the bond that is more polar. All right, now we're going to look at another set. We have OF versus OI. Generally, the rule is the farther away from each other they are, the more polar. O and F are neighbors. They're both a couple of big old electron hogs, but they're neighboring hogs, so they're going to share pretty well, versus oxygen and iodine, which are not so close. So your answer is oxygen and iodine is more polar. Let's take a look at the next set. Nitrogen and oxygen versus sulfur and oxygen. Well, let's find these guys on the periodic table. Here we have nitrogen and oxygen. Here we have sulfur and oxygen. Well, I didn't mean to include phosphorus in that. Both nitrogen and oxygen are both a couple of hogs, so they're going to share pretty well, which means sulfur and oxygen are not going to share as well. So that one is more polar. I wouldn't call it extremely polar, but as compared to nitrogen and oxygen, much more polar. See if you can do this next one on your own. Okay, well, I'm going to put hydrogen where he belongs in terms of electronegativity. Hydrogen sits right here. So we have nitrogen and hydrogen versus silicon and hydrogen. Well, silicon and hydrogen are neighbors. They're about the same size. So these guys would be nonpolar, much more so than nitrogen and hydrogen being different sizes, and nitrogen being that big old hog that it is, that one's going to be more polar. Okay, we're going to do it again. Which one do you think is more polar? And why? Well, if you said hydrogen and fluorine, you're right, because we just went over that a minute ago. OS versus OF. Well, O and F are neighbors, so they're going to share pretty well. So this one's more polar. NS versus NCl. Pause it, see if you can do it. That's right, this one's more polar. N and S are not neighbor, well, I mean, they're neighbors, but and they are going to be polar, but these two are much farther apart. So that one's more polar. CS versus CL. Basically for the same reason as C, this one's more polar. The next thing I'm going to talk about, dipole moments.